Once you have filled the pipe, maybe you have overestimated, but even overestimation leads to keeping the pipe full. But once you have filled the pipe, you need to ensure that you don't put a packet unless a packet has been removed. So this is what is called conservation. And this is even more important when you have overestimated, that is, you push the network into congestion. So if you're doing self-clocking, when do you think you will put a packet before you remove the packet from the network? Naturally, when you're doing slow start, when you remove one packet, you are putting two packets in its place. So definitely you're putting a packet before the previous packet was removed. Apart from this, do you think there are other occasions where you can potentially put a packet before a packet is removed? So the hint is sliding window and perceived loss. So this can potentially happen in case of timeouts. So when a timeout happens, you are basically concluding that the packet is lost. In other words, it is dropped by some router, thereby it is not there in the pipe anymore, thereby let me put an additional packet. But then these timeouts are a function of the round trip time. And if you do a miscalculation of the round trip time, you can time out even when the packet is still in the network. Suppose you set your timeout value equal to 200 milliseconds, which let's say is twice the round trip time, which is 100 milliseconds. So you're expecting an acknowledgement for this packet after 100 milliseconds and you are ready to wait even 200 milliseconds. But if you don't receive this acknowledgement, you are concluding that the packet is dropped and thereby you are going to resend the packet. But when a network is congested, the round trip times are going to increase significantly because there is a lot of queuing. So the packet is still in the network, maybe it is stuck at some router, in which case, in this case, the round trip times may be 400 milliseconds. But your timeout value is wrong. So the packet is still in the network and now you have put an additional packet, which is the retransmission of the packet into the network. So this is what we call out of the frying pan into the fire. As is, the network is struggling to get packets out and now you are dumping retransmissions and making its life worse. So it's very important to ensure that the delayed packets not be interpreted as lost packets. So for this, the RTT calculation is very important. So this was the algorithm that was used originally in the TCP implementation, but this led to network collapse. Later they revised it, but let's understand this original algorithm first. So when you send a segment with a sequence number and you get an ACK acknowledging this particular sequence number, you can calculate the round trip time. This is called the sample round trip time. Then you calculate an estimated round trip time. This is nothing but a weighted average where you give a weight of A to the estimate and a weight of 1 minus A to the current sample. So naturally, if you use a small value of A, you are going to react to the temporary fluctuations. That is, you are giving more weight to the current samples. On the other hand, if you use a large value of A, you are not very quick to adapt to changes. The original algorithm chose a value of A between this and this because it didn't want the temporary changes to affect the estimates. And the timeout value was chosen as twice the estimated round trip time. So this factor accounts for the variability in the round trip time. So this works fine when the variability is small, but when you have network congested, the variability is going to be rather large, and it was turning out that you were retransmitting packets which were only delayed. So Jacobson and Kerels proposed a new algorithm that calculates round trip time, and this algorithm takes into account the variance of the round trip times. Basically, if the variance is small, you can trust the estimated round trip time. On the other hand, if the variance is large, the timeout should not depend heavily on this estimated round trip time. So that's the logic. So thereby you are now going to use this difference variable to determine the difference between the sample round trip time and the estimated round trip time. Like before, the estimated round trip time is nothing but a weighted average. This is just a different way of writing the same equation as earlier. But now you are maintaining a weighted average of the difference also. This is being captured by this equation where this is the estimate of the difference. In their implementation, they chose a value of D equal to this. where the timeout is dictated by this equation, where you are considering both the estimated round trip time as well as this weighted average of the difference. And the U and Q are chosen as under. Now suppose your deviation is very small, then this factor tends to 0, in which case your timeout is dictated by your estimated round trip time. Notice that in this case, when the load is less, your timeout is estimated round trip time plus a small constant. It's not twice the estimated round trip time as was being done earlier. So if things are relatively stable, you react to losses quicker. But on the other hand, if the round trip variation is large, then this term is going to dominate. And your timeout is going to be dictated by this. And this worked out quite well in the TCP implementation. I should also mention this other thing. Suppose you send a packet, it got lost, so you timed out and you're retransmitting the packet. Let's say this also got lost. So when do you retransmit this particular packet again? That is, retransmit the retransmission. So if you notice, during this time, you're not getting any sample round trip time measurements. So you have to act accordingly without the sample round trip times. So what is done in implementation then is what is called exponential backoff. In other words, if your timeout value here was 1 second, here before you retransmit this retransmission, you wait for 2 seconds. If this were also lost, you will wait for 4 seconds before you retransmit it. The reason for this comes from control theory. It's called exponential damping. Any unstable system can be stabilized by adding exponential damping. What does it mean with respect to networks? So currently the network is congested, so it is in a state of congestive collapse. If you want to stabilize this system, you need to introduce exponential damping to its primary excitation, which in this case is the traffic sources. Basically, give enough time for the system to recover before you send packets. So coming to adapting to the path, so you do slow start to begin with, you are bound to overestimate and you are going to push the network into congestion. During this phase, you use this round trip time calculations so that you don't make things worse, but you do need to correct your overestimate. And in that process, you may underestimate and you need to correct that as well. Not just that, your available bandwidth is also going to vary with time, just because the network is dynamic, in which case you need to adapt to this as well. So basically, you need a feedback mechanism from the network that says that your estimate is wrong. So what can this feedback mechanism from the network be? What are your thoughts? So let's look at overestimation first. We know that overestimation leads to congestion. So what is the feedback that the network can give whereby you can figure out that the W you chose was an overestimate? Now, if you're thinking the routers can inform the senders about the congestion and thereby they can cut down on their sending rate by reducing the W, the routers do no such thing. Though I mentioned there is the source quench message, it's not used in practice. So what other mechanism can you rely to get a feedback that the network is congested? You can answer this, it's not difficult. The answer is timeouts. If losses are invariably due to congestion, again, since we are dealing with wired systems, the losses due to errors we can ignore because the bit error rate on wired links is extremely low. And if your timers are working correctly, by timers I mean the timeout timers, then the timeout invariably means that some congestion is happening as part of the network because your packet was lost. So if a sender experiences a timeout, it can view this as a signal that there is congestion in the network. Suppose you are operating with a window size of W and then the sender timed out, whereby you are concluding that the network is congested. Now, how do you change this estimate? Do you do what is called an additive decrease, by which I mean you decrease it by a constant value, or do you do what is called a multiplicative decrease, that is you decrease it by a factor of C? So what are your thoughts? Greediness doesn't work here. You do need to do exponential damping like I have mentioned before. So if you push a network into congestion, you need to give it enough time for it to recover. So you do need to reduce your sending rate significantly. So this is what you do. If this was your past estimate, you cut that window by a factor of d, where here d is selected to be equal to 0.5. In other words, if your window size was 10 and you detected congestion, you set it equal to 5, which is 10 over. Maybe the correct window size is 7. So when you do this, you are underestimating. That is going to lead to lower utilization. Let's say you chose 5, that is W is equal to 5, and then the congestion went away, and you can potentially use a W of 15. Unless you correct your estimate, you are not going to reach to this 15 value. So you need to increase this estimate. Now the question is, do you do an additive increase? In other words, do you increase this estimate by a constant value, or do you do a multiplicative increase? That is, you multiply it with a constant value. You can't be greedy still. If you do a multiplicative increase, again you're going to push the network into congestion, and overestimation is inevitable in here. So what is done is an additive increase where you increase this value by a constant value. So often what is done is you increase your window by one segment every round trip time. So you're being careful, you're slowly probing the network to see if you can get some more bandwidth. So this summarizes it. This is called congestion avoidance, additive increase, multiplicative decrease. On detecting congestion, you set your congestion window to half. And after this point, whenever you receive an acknowledgement, you're going to increase this congestion window by 1 over congestion window. This is the additive increase portion. Wait, you said increase by 1 every round trip time. What is this? So if things are going fine, how many acts will you receive in one round trip time? Basically, how many ever you sent in the previous round trip time, which will be equal to CWND. Thereby, in this process where for every act that you receive, if you increment it by this amount in one round trip time, you are going to increase the congestion window by one segment. Well, if you're wondering why not just do this, this fits in well with the self-clocking approach. Otherwise, you will have to set some timer to increment it. In this case, whenever this act event happens, you can automatically increment. So this congestion avoidance results in this sawtooth based behavior where you increase the congestion window additively over time till you hit a point where you hit congestion, and there you cut it by half. So this is 10, so you cut it by half to 5 and again probe additively. So again it increases linearly and it will again hit congestion. As you can see, at some other point here you are able to increase it a lot more than before because of the traffic patterns, and again you cut it by half when you hit congestion, and again you probe. In this case you didn't go as much as before and you hit congestion much before, and thereby again you cut it by half and then again you increase. Now that we have seen the mechanisms, we will put it all together up ahead in the TCP versions. To summarize, this congestion control is a very difficult task. You need to choose a window size that prevents underutilization. At the same time, it does not cause congestion, and at the same time you get the fair share of your resources. TCP does this beautifully. Notice I'm not using efficiently. In fact, all these techniques are really beautiful in nature. Well, what can I say? TCP is my favorite protocol. To this day, when I dig into TCP, I always find something which I have not realized before. It's full of subtle issues. So getting back, it uses these variety of techniques: slow start, good round trip time estimation, congestion avoidance, to handle this congestion control problem. As I mentioned, we will put them all together and work out some examples to see how the TCP actually works.